Everything you've been taught about earthquakes says silence is the good sign. But on this fault, silence means something has already broken, completely, permanently, and the parts still making noise are the ones still fighting to hold on. Stick with me, because once you understand why that's true, the way you read every earthquake map for the rest of your life is going to change. Let's get into it. Start with the basics, the way most of us were taught to think about faults. A fault that's rumbling, that's producing small earthquakes on a regular basis, feels dangerous. A fault that's dead silent feels safe, like it's resting, like the pressure isn't building. That instinct isn't wrong most places on Earth. But off the coast of Vancouver Island, at the northern tip of the Cascadia Subduction Zone, that instinct gets flipped completely on its head. And the reason why is one of the strangest and most important pieces of earthquake science to come out in years. Here's the setup. 12 days apart, in essentially the same patch of seafloor, two earthquakes struck at almost exactly the same magnitude, both right around 5. 5 to 5. 6. The first hit late in the evening on July 19th. The second hit late on the night of July 31st into August 1st. Both were centered roughly 200 kilometers southwest of Port Hardy, on the northern tip of Vancouver Island, at a depth of about 10 kilometers. Both produced light to moderate shaking on land, with no damage and no tsunami threat. Both were felt hundreds of kilometers away, one reaching all the way into Metro Vancouver, the other felt as far south as Everett, Washington. On paper, that's two routine moderate earthquakes on an active plate boundary. Nothing that should make headlines on its own. But the location is what makes this worth 20 minutes of your evening, because both of these earthquakes landed inside a structure that scientists have only just learned is in the process of tearing itself apart. That structure sits at the meeting point of two tectonic plates most people have never heard of. The Juan de Fuca plate is the big one, the one responsible for the looming, feared Cascadia megaquake that could eventually reach magnitude 9. But right at the northern edge of that plate, there's a much smaller piece of crust called the Explorer plate, wedged between the Juan de Fuca plate and the Pacific plate. The boundary between the Explorer plate and the Juan de Fuca plate is called the Nootka fault zone, and it's exactly where both of these recent earthquakes occurred. For decades, scientists assumed this boundary was simply a transform fault, a place where two plates slide past each other horizontally, similar in principle to the San Andreas fault, just underwater and much less studied. But in 2281, a research vessel called the Marcus G. Langseth sailed out to this stretch of ocean and conducted something close to an ultrasound of the seafloor, using seismic reflection imaging, sending sound waves down into the crust, and recording how they bounce back. Combined with detailed records of small earthquakes collected over years, a team of scientists led by geologist Brandon Shuck put together the clearest picture anyone has ever had of what's actually happening beneath the patch of ocean. And what they found was not a simple sliding boundary. It was a subduction zone in the process of coming apart. The images revealed tiers cutting straight through the descending slab of oceanic crust, including one massive break where the plate has dropped by roughly 5 kilometers. Think about that for a second. 5 kilometers is not a small offset. It's a step inside the Earth's crust taller than almost any mountain on the surface of the planet, hidden beneath the seafloor, invisible unless you know exactly where and how to look for it. The researchers found that this tier runs for roughly 75 kilometers along the boundary between the Explorer and Juan de Fuca plates, and geodetic measurements, the kind of precise satellite positioning that can detect millimeters of ground movement, show that the small Explorer plate is being pulled downward at less than half the rate of its larger neighbor. It's not moving in lockstep anymore. It's being left behind, progressively isolated from the mechanism that used to drag it down at the same pace. Shuck himself described it in a way that stuck with almost everyone who covered the research. He said, "This is the first time scientists have a clear picture of a subduction zone caught in the act of dying, and that rather than shutting down all at once, it's ripping apart piece by piece like a train slowly derailing one car at a time." He also made the comparison that starting a subduction zone is like pushing a train uphill. It takes enormous effort, but once it's moving, it's like the train is racing downhill, essentially impossible to stop. Ending one, he said, requires something dramatic, a train wreck. And off the coast of Vancouver Island, that train wreck is happening right now. Slowly, in a way we've genuinely never been able to observe this clearly before on any subduction zone anywhere on the planet. Now, here's the detail that inverts everything you think you know about reading a seismic map. And it's the whole reason for the hook I opened with. Along that 75-kilometer tear, some sections are seismically active, rumbling with small earthquakes on a regular basis. Other sections are completely silent, and the interpretation researchers have offered for those silent stretches is the opposite of what most people would assume. Once rock is fully separated along a break like this, it no longer has contact across the fault. It no longer sticks, it no longer stores strain. Because it isn't storing strain, it has nothing left to release. So silence in these specific segments of the tear isn't the reassuring sign it would be almost anywhere else. It's evidence that the tearing there is already complete. The break has already happened. The two sides of the plate have already come apart at that spot, and there's simply nothing left there to make noise about. Flip that around, and the sections that are still active, still producing small earthquakes, still rumbling, are the ones that haven't finished tearing yet. They're the parts of the plate, still holding on, still under stress, still fighting the separation that the quiet sections have already gone through. In most of seismology, quiet is the reassuring color on the map. Here, in this one very specific structure, quiet means the opposite. It means the job is already done in that spot. Noise means the fight is still happening. That's the frame you need to hold on to understand why these two recent earthquakes actually matter. Because a tear like this creates what geologists call a discontinuity, a break in the continuity of the plate. And discontinuities are exactly the kind of feature that can behave as a barrier, a place where a rupture running along a fault might be forced to stop. Or, alternatively, a decoupled block on one side of that discontinuity could remove a restraint, letting the segment on the other side load up faster and eventually fail harder than it otherwise would have. Nobody currently knows for certain which of those two scenarios is closer to the truth for Cascadia. What these two recent earthquakes provide is a small, genuinely useful piece of observational data toward answering that question, because the pattern of where earthquakes cluster along this tear, whether they migrate and whether the silent stretches stay silent, is precisely the kind of evidence that eventually settles it. Before we get to what happened with these two specific quakes, it's worth pausing on just how unusual it is for scientists to catch a subduction zone doing this at all. Most of what we know about how these boundaries die comes from studying ancient, long-dead fragments of crust preserved in the geologic record, tiny scraps of old plates scattered around the planet that hint at how they must have broken apart millions or tens of millions of years ago. Nobody has ever been able to watch the actual process happening in something close to real time, with modern instruments recording every twitch of it. That's what makes this stretch of ocean off Vancouver Island so valuable to researchers. And it's also part of why these two recent earthquakes carry more weight than their modest size would otherwise suggest. They're not just two more entries in a long list of routine Pacific Northwest earthquakes. They're two fresh data points arriving directly on top of a structure that, until very recently, nobody even knew was actively tearing. Let's talk about what actually happened with these two specific quakes, because there's a part of the story around them that deserves its own explanation. And it's not about the shaking. It's about how confusing it was to even figure out how big the second earthquake actually was in the first place. For roughly 20 to 30 minutes after the August 1st event, the United States Geological Survey's public feed showed essentially nothing. Other systems picked it up first, with early estimates bouncing between different values as more data came in. Different agencies were publishing different preliminary numbers. And for a little while, the same earthquake carried at least 3 or 4 different magnitude values, depending on which source you happened to be looking at. If you were watching that unfold in real time, it's completely understandable why it looked suspicious, like something was being managed or downplayed behind the scenes. But the actual explanation is far less dramatic and, honestly, more interesting once you understand it. Different agencies run different automated systems, pulling data from different networks of seismic stations, and for an earthquake sitting out in the open ocean, every single one of those stations is on land, meaning the wave arrives at all of them from roughly the same direction. That one-sided geometry genuinely starves the calculation of the kind of information that makes magnitude estimates converge quickly. Depth is often assigned a default value rather than measured precisely for events like this, and the magnitude estimate itself tends to drift as more distant stations report in, and the algorithm has more to work with. Crucially, the way this particular sequence resolved, the number ultimately settled higher than where it started, not lower. A process designed to suppress or hide the true size of an earthquake would not end by revising the number upward. This was simply several different computer systems doing arithmetic on incomplete information and publishing their working estimates in public while the picture was still coming into focus. Once a seismologist actually reviewed the data by hand, the number landed right around 5.5 to 5.6, which is where both agencies ultimately agreed. There's something else worth sitting with about these earthquakes, and it has to do with why officials were able to rule out any tsunami risk within minutes of both events. A tsunami isn't caused by shaking itself. It's caused by a large volume of ocean water being displaced vertically, which means the seafloor itself has to move up or down. That's exactly what happens during a megathrust earthquake, the kind Cascadia is famous for and feared for, where one enormous block of crust rides up and over another, lifting the entire seafloor and everything above it. The Nootka fault zone doesn't work that way. It's dominantly a transform boundary, meaning the two plates are mostly sliding past each other horizontally rather than one riding over the other. Confirmations from the agency responsible for that stretch of coastline described the August earthquake as having been caused by mainly sideways movement along a near vertical fault. When you push water sideways instead of lifting it, it doesn't pile up into a wave. It simply flows around. So even though these earthquakes and a future megathrust rupture on the locked interface south of here could theoretically carry the exact same magnitude number, they are fundamentally different animals with fundamentally different consequences because of the direction the rock actually moves. That distinction matters even more when you look 200 kilometers south of the Nootka fault zone to the part of Cascadia that people actually worry about when they talk about the big one. That's the locked, brittle, shallow section of the megathrust, the part of the interface where the Juan de Fuca plate and the North American plate are essentially glued together by friction, accumulating strain that hasn't been released since the last great rupture back in the year 1700. Beneath that locked zone, deeper down where the rock is hotter and under enormous pressure, there's a transitional layer that behaves completely differently. It doesn't snap. It creeps, sliding just a few centimeters every so often over the course of days to weeks. You can't feel it happening, but it generates a low, quiet seismic hum called non-volcanic tremor, and the associated slow, gradual movement is known as episodic tremor and slip. This phenomenon was first properly characterized on the northern Cascadia margin back in the early 2000s, and it's been cataloged continuously ever since, with recurring episodes showing up roughly every 14 months beneath the Olympic Peninsula in a cycle scientists have tracked for over 2 decades now. Here's the part of this that reverses almost everyone's intuition, and it matters just as much as the tear itself. When that lower portion of the interface slips during one of these episodes, it does not relieve stress on the locked zone sitting above it. It transfers stress onto it. Each slow slip episode advances the plate boundary underneath the locked patch, which leaves that patch further behind, more strained and not less. So tremor activity isn't a countdown clock ticking toward disaster, and it isn't a warning sign in the way people often assume. It's closer to a stress gauge. When tremor is actively running, the loading machine is running, and stress is being added. When it goes quiet for a stretch of days, the locked zone stays exactly where it was, still locked, still holding on to every bit of strain it had already accumulated. Nothing gets released during a quiet period. The loading simply pauses while everything already stored stays stored, waiting. Around the time these 2 recent Vancouver Island earthquakes were making news, activity elsewhere along this same broad plate boundary system was also shifting, and it's worth walking through carefully without overstating what any of it actually means. Farther south, in Northern California near Cloverdale, an earthquake swarm has been building, dozens of events over the course of about a week, including a moderate quake in the low 4s, and a scattering of smaller ones, clustered close together in both time and location. What's genuinely a little odd about that cluster is the shape of it. The events are strung out roughly west to east, but the mapped faults running through that part of Northern California mostly trend north to south. So the swarm sits at close to a right angle to the structures geologists would expect it to follow. There is an obvious, mundane explanation available. That area sits right on top of an active geothermal field, where wells pull heat out of the shallow crust to generate electricity, and induced seismicity, earthquakes triggered by fluid injection or extraction during energy production, is a well-documented feature of geothermal operations around the world. Whether this particular swarm is related to production, related to an underlying fault structure nobody's mapped in detail yet, or simply coincidental timing, sitting right next to a real tectonic tear, remains genuinely unresolved. Further south still, near the point where the Garlock Fault meets the San Andreas, a stretch of ground that had gone quiet for a while suddenly produced a small burst of activity, and near Desert Hot Springs, activity picked up right beside a segment of the San Andreas that hasn't ruptured in well over a century, and has therefore been quietly accumulating strain for longer than modern instruments have even existed to measure it. Now here's the part that has to be said clearly, because it would be easy and genuinely tempting to connect all of these dots into one single dramatic story, and the physics simply doesn't support doing that. An earthquake off Vancouver Island did not reach down the coast and trigger a swarm in Northern California, and it certainly didn't nudge anything along the San Andreas hundreds of kilometers farther south. The physical mechanism that would allow one earthquake to permanently change the stress on a fault that far away falls off extremely steeply with distance, and at the range we're talking about here, the effect from a moderate magnitude 5.6 earthquake is essentially negligible. There's a separate, faster-acting mechanism where the actual passing seismic waves from a very large earthquake can nudge a distant fault while those waves are physically moving through it, but that effect requires a much bigger earthquake than what happened off Vancouver Island to matter meaningfully at continental range. None of that applies here. So what's the honest connection between all of these separate pieces of activity happening in the same general window of time? It's simply that they're all playing out on the same enormous, continuous machine. The west coast of North America isn't a patchwork of separate, unrelated local hazards that happen to share a coastline. It's one long connected plate boundary system, running from the transform faults off British Columbia, down through the locked megathrust beneath Washington and Oregon, into the fragmenting terminus near Northern California, and onward into the strike slip faults of Southern California. Vancouver Island and California aren't links in a chain where one event causes the next down the line. They're separate instruments, spread out across the same enormous machine, each one recording its own small piece of that machine's ongoing restless behavior. The reason to look at all of them together in the same breath isn't because one caused the other. It's because the machine itself is the actual story, not any single earthquake sitting on top of it. So where does that leave us? And what should you actually watch for as this continues to develop? There are a handful of specific things that will genuinely tell us more, and all of them resolve on a timescale of days to weeks rather than centuries, which is refreshing in a field where so much unfolds over geological time. The first is the pattern of aftershocks following the August earthquake. The question that matters isn't simply how many aftershocks show up. It's where they show up. If they cluster tightly around the original epicenter, that's the ordinary expected outcome, and it tells us the rupture stayed contained to a small patch. If instead they migrate along the strike of the fault zone, tracking the same direction the underlying tear runs, that would be a meaningfully more interesting and more significant result, worth paying close attention to. The second thing to watch is the fully reviewed mechanism behind the August earthquake, the detailed technical analysis of exactly how the fault moved. Preliminary readings pointed toward the expected sideways, strike-slip motion consistent with a transform boundary. But a full seismologist-reviewed confirmation carries real weight, because if the final analysis turned up something unexpected instead, it would change how researchers interpret both of these recent earthquakes and potentially the broader tear itself. The third thing worth tracking is the tremor beneath the Olympic Peninsula, the slow, silent signal of stress loading on the locked megathrust to the south. There's an idea circulating that a nearby large earthquake near the Nootka fault zone might temporarily desynchronize or disrupt that tremor cycle. It's not an official agency-confirmed finding, and it's not something published in a peer-reviewed paper yet, but it is genuinely testable using public data over the coming weeks, which makes it a rare case of an online claim that actually comes with its own built-in way to check whether it holds up. And the fourth thing is that swarm down near Cloverdale. If it keeps producing earthquakes along that same unusual west to east line at similar shallow depths over the following days, the geometry stops looking like a coincidence and starts looking like a genuine structure worth mapping and explaining properly. If it fades out the way ordinary earthquake swarms typically do, then it was exactly what it looked like on the surface. Background noise from an active geothermal region, nothing more. Underneath all four of those threads sits the same larger question that's been open since researchers first published this tearing plate discovery. We can now see, with a clarity nobody has ever had before on any subduction zone anywhere on Earth, that this one is coming apart. We've imaged the tiers directly. We can measure the smaller explorer plate falling behind its larger neighbor in real time using precise satellite data. We know that some stretches of this 75-kilometer break are silent specifically because the tearing there is already finished, and we know that the parts still making noise are the parts still fighting to complete that same process. What nobody can currently answer, because there's no second identical example anywhere else on the planet to compare it against, is exactly what a fragmenting northern edge does to the rest of the machine sitting south of it. The locked megathrust that everyone along this coast genuinely worries about. Two nearly identical earthquakes, 12 days apart, both landing inside that same tearing structure, while the interface 200 kilometers south spent most of that same stretch of time quiet, and faults at the far southern end of the whole system started stirring in their own separate, unconnected way. That combination isn't a warning, and it isn't a countdown clock ticking toward some specific date. It's genuinely valuable, hard-won observational data on a system that has never once been instrumented this closely, while it was actively coming apart in real time. Scientists will be watching where the aftershocks migrate, what the fully reviewed mechanism ultimately shows, and whether that tremor cycle beneath the Olympic Peninsula behaves any differently over the coming weeks than its usual 14-month rhythm would predict. If you live anywhere along this coast, from Vancouver Island down through Washington, Oregon, and into Northern California, none of this changes the practical advice that's always applied to this region. Know how you'd respond if strong shaking starts. Drop, take cover, and hold on until it passes. And have a plan for your household that doesn't depend on being near your phone when it happens. This isn't a reason for alarm on any particular day, and nothing in this data points to a specific date or specific coming event, no matter how tempting it might be to read one into it. It's a reason to understand the ground beneath this coastline a little better than you did before you started watching, and to appreciate just how rare it is that scientists are getting to watch one of the planet's great tectonic structures fall apart, piece by piece, while the instruments are actually running. I'll keep tracking the aftershock pattern, the reviewed mechanism, and the tremor count as the data comes in, and I'll bring you the numbers the moment there's something genuinely new to report. If anything changes in the coming days, whether that's a new aftershock cluster, a revised mechanism, or a shift in the tremor pattern beneath the Olympic Peninsula, you'll hear about it here first. Thanks for watching, and I'll see you in the next one.